Hello, everyone. I'm Vicente Guayart. I am one of IAC founders, right now director of the Baidaura Labs at IAC. Today, we are very happy to have here with us Firas Safieddine. He's an architect from Lebanon. I met Firas first time when he was studying at IAC. He came to IAC to study in the Master of 2 years, 2015 to 2017. And he was one of these typical IAC students that was doing illegal things at the building. So he basically make a box and make a kind of a small building inside the second floor, what was kind of hard to do because he was moving up and down the materials, and he was testing something like a kind of machine with some sensors in the brain that at the end this became his final project that was called Brain Space. After that, we have been working together in several projects, and he has been doing amazing things with programming, rendering, modeling, and so many other things. And right now he's doing. Then suddenly we discover he was not only good on drawing, representing, modeling, and so on, but also when everything related with metaverse started, like in fact explode like 2 or 3 years ago, he told me that he was writing a book about that, and then this book will be published by Actar, that, as you know, is one of the most important publishing company for architecture in the world. The book is called Metaverse Urbanism. Spatialization takes command. Metaverse Urbanism, not notes on future urbanism to the metaverse and life as we live it. So we are waiting for the book to see how good is writing Firas, and but I am sure it will be great. He recently has created a company in China called Spatial Force with some other partners that are IAC alumni. So I would say that Firas is the kind of guys I am very proud that IAC has helped to educate and to mature, and also as we do always, we try also to support the IAC students to grow and to have a big impact in the world. So we think will be a big impact with the artificial intelligence and what is coming behind. And it's very important, even if this is a kind of blur thing that is not defined yet. This is where IAC like to be. That's why we are advanced. We like advanced architecture, and that's why, yeah, I am super happy to have today with us Firas. Firas, the floor is yours. Thank you.
I mean, it's an honor and a pleasure to be presented by Vicente, so thanks a lot for the introduction. And I think I will straight away jump into the presentation because they just told me we only have 40 to 45 minutes and we have a lot of things to cover. So just to give you a bit of a brief on how it's going to be today, I'm going to be showing you specifically projects that we have been going through on AI, but as well I'll be taking things more specifically on a new way of seeing what AI is, because I believe as architects, we on the first hand define what these technologies are for us to inform the discipline, and then on the other hand, act upon these by understanding how they work and so on. So let's just start.
Big data, machine learning, blockchain, artificial intelligence, digital manufacturing, big data analysis, quantum communication, and Internet of Things.
This is unfortunately how we see these terms these days kind of jammed together in a way that everybody is saying AI and artificial intelligence and machine learning and deep learning and all these kind of things. And they usually come in a way that is very misunderstood because people just put all these words into one container. They are cool and they are buzzwords, but we have a different say. And this actually started by this book, which probably most of you would know, which is Being Digital. But there's one thing that is this book inspired in me, which is the idea of digital being, which is not only on how we can be digital in the digital era, which was probably very hot in the 90s, but then going forward with all the technology we are seeing now and the immersivity that we can have, the idea of digital being becomes plausible and viable. And then this is one thing we are thinking about a lot. Another one is this. This is my main fascination, that in the last century, we have been very much on mechanization. And then probably the next century is going to be about spatialization. Mechanization was great, but then the one thing it enables and one thing where we architects are operating the most is spatialization, making things spatial and thinking about spatial organizations in this. And I would like to probably start from this. This was actually kind of moved by a conversation we were having, and the conversation goes about buildings and architecture and if they're the same thing or not. And I think we have been, with recent technologies, proving more and more that buildings and architecture are worlds apart. If one thing is happening with technology, is every time architects are going one step away from the building to the essence, which is creating interiority. I made this using a BCI typing, so I was typing with my brain. As you see, it's totally hand-free, as a statement that probably in the future we'll be creating architecture in this way. This is just an index for the presentation. We're gonna do three things. We're gonna go on what is AI, how is AI actually working, and then why is AI used by architects? And that's the part where I'm gonna show you some of the projects that we've been working on. The starting point is from Geologics, which is a book by Vicente, and this book has inspired a next move, because if the first move was about geologies and information and geographies and architecture, probably the next move will be about biologics, which is how minerals and biology can create intelligence and how we can create architecture using these kind of concepts. So I've been recently working on the topic of electrical ecologies, which is a kind of discourse commenting on dark or black ecologies, which understands everything as nature. And the main reason of this is electrical ecologies activates that. It works on the electrical layer, which stems from one basic understanding that minerals become technology. And then with the help of these technologies, naming as electrical objects, we can do intelligence, be it synthetic or mineral, as we will call it now. So going from PCBs to brains, and then neurons are neurons. The idea is how using these neurons we can spaces which are suddenly represented in a tectonic manner, that then develops to kind of go back and look at architectural drawing, how we represent things, previous styles, history, emerging things, and so on. All this video has been generated by AI, by the way, and it's a new way of thinking of what architecture can be in that sense, where we have tools now to go from text to 3D, 3D to text, text to image, image to 3D, image to sound, and all these types of things, which we have been using in a lot of what you will see next. So electrical ecologies understands the world, and specifically the world we live in with intelligence, in three phases. We have charged matter, we have electrical objects, and we have the neural objects. So charged matter is everything from electric jars to ions and copper wires and all the matter that we have. Electrical objects are circuit boards, phones, computers, and all of these are made actually from minerals. And then we have neural objects, which is be it biological or mineral. They both have intelligence emerge from them. We can talk about artificial intelligence or brains, but at the same time, there's something happening now, which is artificial neurons, where we have brain cells or neurons grown in the lab. And this is a video showing how they can learn to play Pong. And for me, the main reason why I'm using AI is for one simple thing. If we understand the world as things moving from being charged matter to electrical objects to neural objects, then we need to understand is that if all the neural objects are electrical objects, fundamentally, we don't have any proof otherwise. But not all electrical objects are neural yet. And what we are doing with AI is, or intelligence itself, is giving intelligence to this circuitry to make things neural. So our job as designers is actually to move things from being electrical objects to neural objects. So fundamentally, electrical ecologies is about this specifically. It's about designing the electrical layer, which is available in every kind of material assemblage. Because of one fundamental thing, that the world we live, be it digital or virtual, has a very strong physical foundation. These are sulfur mines, cobalt mines, or otherwise. And this is a map showing how mining kind of consumes the planet in a way, and consumes the world, where we have technically infinite mining sites. And even the internet, which is the foundation of a lot of how we live today, the internet is actually hardware. Internet is a bunch of cables running the planet and consuming the oceans and the territories. So if this is the foundation, traceability becomes very important and very political. This is an image that I was doing just to send the message. As you can tell already, on the left, you see all the mining sites in the world. In the center, you see an iPhone where it comes with extraction facts, just like any chocolate bar would have nutrition facts. And here you would see how much impact it has and how much footprint, and you see the ingredients, and then we start to understand how all these technologies have a very strong physical foundations that make it possible. So let's go to the first question, which is, what is AI? If we ask this question, let's break it to two words and understand first, what is intelligence? Before diving into this, intelligence, as we saw before, what I'm trying to establish here is that it's an emergent property of material assemblages. This is something probably I'm going to tattoo very soon for the times I have been repeating the statement. But this is something that is very, very fundamental why we work, and probably some of you have spotted why. It's because architecture as well is technically material assemblages. So if intelligence is that, then as architects, we have a lot of things to do. And that's why I'm saying the word mineral here. These are the three words probably that have been kind of moving around: artificial intelligence, synthetic intelligence, and mineral intelligence. But as we believe, and as, I mean, this design direction takes us, we believe that everything is natural. Otherwise, it would be very hard to understand what is natural. This kind of 100 years old dogma of nature as something that is out there has been over. Artificial intelligence, unfortunately, is a very tricky term, which deals with the artificial, which is a very hard thing to define. And for us, kind of as well, everything is real. And this keeps us with one term, which is mineral intelligence, which takes either biological or mineral intelligence as the two forms of intelligence. So in that case, I will go for a very, very simple definition, where mineral intelligence is simply the emergent property or phenomena of any material assemblage to make and enact decisions in an environment based on learned patterns. So in even more simpler words, AI or MI is the decision-making capacity for machines based on learning. So let's go to the second chapter, which is, how is AI working? You've all seen a lot of different AI models, from generating chairs to tables to assisting reading to reading numbers to interpolating between objects, aiding people play music and recognition and so on. And we've all probably, I see a lot of designers here, we've all played with these kind of beginner games. We were doing, and myself included, these are the proof. We have been kind of playing around with training models based on images, on architectural styles, and to see how AI can produce new architectural styles based on mixing features. These are like numerous trials. And my fascination with neuroscience took me one step ahead, which is to understand if AI can actually create features that are based on a training model. So here I was training based on a huge data set of brain scans. And I was seeing if AI can figure out which brain scans have tumors and which don't have tumors. So we were generating numbers and numbers and numbers of brain scans with tumors and without tumors to see the precision of the experiment. And to go for how AI works and how it works, I'll show you some of the lessons that we learned as well. The first lesson is noise. Noise is where all AI starts. Every time an AI is learning something, especially in the generative models we're using here, is starting from noise and then getting better and better and better. By the way, this is probably the first thing I produced with AI ever, some years ago. That's another fun project we were working on as a comment on representation, because if we understand one thing, we understand that if things are electrical, then probably they don't speak our language. AI doesn't speak images or text, it speaks data and numbers. And this is something to be very careful about, because what's happening here is that data is very malleable, and the way we change it and we encode and we decode, we change how things are. What you see on the left is an image that has been represented in the middle and then represented again as a point cloud. And we see how from one perspective it makes sense, from many others it doesn't really. Because in fact, machines understand us more like this. This is a genetic sequence that is encoded in one A4 page, and we see it in a very different way than a computer does. The other thing is biases. This is a project I was working on where we actually took a project called The Sound of Laughter, or The Laughing Boy, by one artist called Esli Casero. And this guy was sharing this image with everybody and asking for people to make their own interpretation of the image, where kids were coloring on top and making all these interpretations. But what we thought is probably we should train an AI using a lot of oil paintings data set and see what AI can produce out of this in the style of a realistic oil painting. And then what we realized is most oil paintings are of white kids. And then what happens if you train it with that? You produce a white kid image. This is not because AI is biased, this is because our data sets are biased. And finally, as function approximating machines, AI works in a very simple ways that are deep layers that kind of together create complexity. Things to highlight here are randomness and features, because how AI understands anything, and not AI here is machine learning, is by understanding features, correlations, and then moving on from this, where we will see now this. So here I'm drawing just a line and a dot. And here we see from randomness, it starts to optimize and optimize and optimize, where it in the end can reach this. So if you can think about what this is in other terms, in a very simple terms, it's actually trying to approximate a function, because for machine learning, probably most things can be represented as mathematical functions in graphs. And what it tried to do is to approximate the function and then fill in the dots to be able to achieve this. And after a lot of epochs, it can reach this line and this. And this is a representation of kind of any model that we can work with. And then third important thing is why AI, right? In the last probably 30 years, with the emergence of computers and digital tools and code itself and intersection with design, right? A lot of discussions in architecture were about, was the saw there? And then we say, okay, what can we do with the saw? And then we invented the table. Or we actually knew that we needed the table and then we invented the saw. This conversation is tricky, because were computers there first and then we saw what we do with them because they were there? Or as designers, we had some disciplinary questions to ask, and then we found computers as relevant tools to use to ask and answer these questions. In my opinion, it doesn't really matter, because both conversations inform each other. We've seen both things happening. But at the fundamental part of why we're using AI and machine learning, other than the two main reasons I was stating, is because of this specifically. This is a Chinese proverb that probably runs in every language. And it's better to teach someone to fish, teach them fishing, than actually to give them a fish. In English, it's if you give someone fishing, you feed them for a lifetime. If you give them a fish, you feed them for a day. And what we're trying to do here is this, is to teach machines how to learn, rather than asking machines to do specific commands. This will allow us to actually generate generative models and things that we then learn from, as you will see in specific projects. So let me move to the second chapter, which is showing you some of the projects that we have been working on, starting by Emergent topographies, which was one of the first projects that we worked on. Leave you with a bit of this teaser, which probably showcases the main features of the project. The project was displayed in Ars Electronica a couple of years back, probably a bit more, some 4 years ago. And then with this project, we were developing a workflow that we integrated in different cities, from Vienna to Barcelona and Saudi and other cities. And the idea here was, as you see, we're using AI to do one thing, to create hybrid data sets that are based on urban data, where we engage community in creating. And then biodata, which is a brainwave data that we were translating to emotions. And then all this data was kind of represented in the same way as you see with all these topographies. And topographies are very flexible things to encode and decode data. So this was a way to understand all these things. We were sonifying these, and then finally we were stacking these into stacks of topographies where we were running classical machine learning algorithms for agents to create this. And this takes us back to the main concept of culture and context, here represented as topographies and brains. For the very specific reason that we said again, which is bidirectional mutation, because it doesn't really matter which came first. Here you see a satellite image of a river that is changing form. It's called meandering rivers. And then here you think, okay, which came first, the water, and then it formed the physical river, the physical channel of the river, or the physical channel of the river was first, and then the water came and followed that channel. And in fact, they both affect each other all the time. And that's applied in a lot of the brain science, neuroscience, and then as well in how we understand things. So this is here, it's very clear to see the workflow. We start with urban data where it's just simulated in the same way that we simulate biodata with daydreams and a lot of different things that we were working on this workflow. Then we were generating all these hybrid topographies. We were generating depth maps out of them, stacking them, generating point clouds, and then mapping them. This was a good exercise for us as well to understand how AIs work, and then working in a way that we can use their capacities to do what we want. I'll just run through this. Probably if you've used the GAN, you know this very well, but for the ones who don't, this is how, starting from a real set of topographies that we feed into the AI and machine learning, starting from noise, it can try and try and try because it works with a adversarial network where we have a discriminator that is evaluating if this image that is produced by the system has enough quality in terms of features, is close enough, and then it will be classified as real or fake. And then we are working with both real and fake images. So you can see data sets that we feed, that we generate, and then fakes that we produce. So with AI models, we were trying different things, injecting more daydreaming data, less daydream data, and seeing the impact of this with randomness and changing features and so on. And that moved us to the second phase of the project where we applied it in Vienna. And then here we're using exactly the same workflow, but it was with new data. Working with biodata and urban data in a different way meant different outcome. Here we were, again, representing, working on commenting and understanding through the work itself on how machine learning works, how representation needs to happen, and so on, following a very clear and simple tooling set which merges GIS, modeling tools, algorithmic modeling as well as neurotechnology and some other machine learning and AI, and then finally representing it through processing that probably some of you know. By collecting all these where we can show topographies in different formats, and then we've been stacking them, producing these hybrid topography point clouds, and then finally bringing all these things together into the artwork that I'll probably leave you with the video too. And then we go to the second project, which actually came out of the same project, thinking about spatiality now. And then this was before all the hype was here. And then we were thinking on how can AI actually create synthetic interiority in the sense of spaces that are fully generated by AI. And actually the main question starts here. We understand things in general as starting from geology, which is probably some billion years ago, several billion years ago, there was nothing other than geology, right? This geology then developed into biology, so we come from geology. And then biology using geology have created technology, which is all the computers you have is technically humans using minerals to create. And then it's interesting that this is linear. And then once you step into technology and biology is available and geology is available, then all the above is created and collapsed and consumed in a non-linear way. So once we figured out how to make technology, then we were producing and consuming technology, geology, biology simultaneously. And this is where architecture is. We were producing interiorities in various ways. And the main question that this project is asking is, if that's a way to do, then how can geology straight away autonomously create these kind of interiorities and so on? So this is the question is, if we as humans can create interiority, which is what we define architecture as, is how can geology do that? So as this was a very short-term project, it was a hackathon project, which was very kind of compact. We had to be a bit simple and then simplistic in a way where we broke down architecture or interiority into 4 different parts. An enclosure, which is, the space envelope that contains everything. Digital materials, where we had video and animated textures that were kind of applied on these meshes. We had a soundscape that was generated by AI as well. And then finally, a population of digital flora, artifacts, and digital avatars that were generated by AI too. So the way to do this was to generate all these components and break down what interiority or architectural space is, and then do them. And that was probably before it was like very distributed, all these models. But here we were using on purpose various models to make a multi-layer kind of workflow where we can add complexity every time we work on it. So for meshes, we were using GANs. Here we were using text to JPEGs. We're using sample wave models and then text to JPEGs here, and then from JPEGs going to meshes, and then we're using different models for people and avatars and artifacts and so on. And finally, it comes with a user interaction where it's more autonomous, so spaces can actually behave and respond to your location and your position. The more you get closer to objects, the more they start morphing and so on. So I'll run you briefly through some of the outcomes of this. So this is an example of enclosure, which can define new specific ways of doing spatial enclosures. Textures, which raise a lot of questions on how we actually do textures, what do we need, and how we represent that digitally. And then animated textures, which were then applied on these meshes, given the kind of geometrical texture that they already have, resulting in interesting solutions where we then train model to produce artificial flora, artifacts, humans, textures. And interestingly, we 3D printed that enclosure that you see here, which is this one. And then the idea was, and that's how it was exhibited, where people would be in a VR inside the environment, and then they will be holding it in their hand. So they will be in the virtual inside the same object they are holding with their hands, which creates a new kind of feel of how we experience space and new spatiality where scale is totally distorted. These are some of the soundtracks that we were generating. Probably very low res for your ears at the moment, but that's a final outcome where we're joining all these different components of what a space constitutes of, and then the idea was to add always more complexity and more layers. So you see there's an enclosure, a texture, objects, avatars, and so on. I'll take you through one of the very first productions of walkthroughs, or in this case fly-throughs within the space, which kind of shows a new way of embodiment inside architecture and how we can use our bodies to understand this. We were doing different speeds and different intervals, and people were moving in different ways. Some of them were autonomous, some of them were attractor, some of them were just driven by the people themselves, to see how it's going. And one thing that we learned working with all these is that it's not just us teaching machines, but machines teaching us as well. From the very simple things to the very complex things. And this is a project that came out of a very simple question, which is how can we as designers and architects create controlled models where we can produce 3D models, not just images, right, based on a custom data set. this question just went in a million directions, which ended up becoming a workshop that I invite you all, if you want, to can just join us on Discord, where all the documentation is available. This is a workshop that we developed together with Michel Azia and Yasser Sijjab, working with different tools to create our own data sets. And for this, we realized that probably we needed a new Grasshopper plugin, which we're developing with the help of Michel, to produce a kind of already encoded list of 3D models that have specific features. So we're working with feature pools. Let's say we have like 3-4 features. So in this case, we have the position of the legs, the height, and all these kind of things that are parameters that describe the model. But then we were generating things out of these pools straight away. So representation is key, and you're probably all familiar with space topology. But in this case, we're understanding the object that we have as part of that full context. So whatever object we have is actually understood as the points it represents or the locations, because this made us understand very, very simple things in a very different way. So here we see a cube, and then we say, okay, a cube is actually an XYZ representation of voxels, and then if we slice it horizontally, then we get all these slices, which each of them is a grid, and then we can number these, and then we can put an object inside, and then say which kind of points are inside the object, and this will be the object itself. And then we can represent these in different ways. So technically, all these models will become represented as arrays of zeros and ones. That, as you see here, the full thing is just the number of whatever we have as the context, and then the object itself is just a representation for the operation on which voxels to call and which voxels to keep that become the object itself. We're producing literally infinite of these structures, which we're having a random number of feet, and then we're rendering some and experiencing them as built environment. I will just go to up the scale a bit to territorial flows, which is one recent project we have been working on closely with a lot of citizen data science and urban mapping practitioners, together with the ÖBB in Vienna. And then the main question that we ask here is, what is the impact of such technologies on how we see territories and how we represent human activity and otherwise in the territory itself? So for this, we went back to get data and represent it from, as you see here, railway networks, green fitness of chlorophyll with NDVIs, water networks in the territory, and as well, we were mapping wildlife flows to see how animals are moving within the territory where Austria is full of forests. Then we used some AIs to interpret all these using language models, right? So this is the data that we were collecting and representing in very different ways and interpolating. And then we were using here image and text cross to come out with these images. So we were using every data sample we had crossed with a prompt, and then we were getting these that we were then using as territorial flows. That's where the name comes from. The process goes through very simple 3 steps of voxel sampling on whatever we were generating, applying organic growth, and then finally applying some particle systems that bring together all the attractors of the different territories. Let me see if that's going to play. Okay, we can just play it from here. So what you see here is actually a representation of all the AI interpreted things that actually in the process, they have all the data that we've been collecting, training that we've been making, and then all the applications of interpretation using the text and image mixed models to produce all these videos, which then came together and we produced 2 works. One is based on this unfolding and the other is based on layers that probably we'll share in the next. Sorry. And finally, as we don't have much time left, I'll take you to the last project, which is back to reality kind of project where we're starting to understand how these models and these applications can be applied in real life scenarios for very specific problem solving. In this case, in healthcare spaces. So for this project, we were bringing together images, user input, and research together as food for the machine learning and AI. And this food was actually helping through text and images, right, feed that AI model which was then producing images. So once the AI model was producing images, we were exposing these images to users, which were sitting and looking at these models. And then from that, we were evaluating how they were feeling using facial expression and eye tracking. And then finally, through analytics, we were able to come up with where they were looking, where they looked more, extract 3 metrics such as happiness, focus, and surprise, and then use these to validate the model and then feed back new input, which was producing better output from the AI. So this kind of feedback loop integrating user experience is something that's key. Here you can see one of the experiments on where people are looking at the image, and here we can tell very clearly. This is obviously a replay video, that's why you see the emotions already there. But you can see here how much milliseconds they were spending on each object, the sequence of where they were looking, all these kinds of things where you can then interpret which parts of the image were actually more effective, more attention attracting, and so on and so forth, extracting what are these objects using the same models as well, and then feeding back whatever made things better back to the model, so then we can create optimized images. I'll show you briefly some of the images that we were generating, where obviously everybody liked more light, everybody liked more greenery, everybody liked more calm spaces, and so on and so forth. And these are perfect examples on how we were optimizing this. But again, images were not enough. So we were trying to play tricks on the models to produce some 3D environments, which was the very first thing we did through depth, which you see on the top was convenient in specific spaces, but was very short to become like really what we would like to do as architects. And here's a way to show just how things were presented in 3D, going from an image which was produced by that feedback loop. Then we were trying to play a different trick, which is to create wide angle images, thinking probably that could be more convenient, thinking AIs could understand these things from better resolution. And we were creating these textured 3D models, what you see on the right, that were, I mean, halfway there, I would say. And then finally, we figured out that probably if we create 360 models of images, we can use these 360 wide-angle images to probably wrap them around these AI-generated models, which ended up being probably the best way to go around it. And in this case, we were creating these healthcare spaces that were coming from all that loop, right, into using AI to produce all of the above, arriving at a 3D space, which was then evaluated by people going into this space in virtual reality, and then we would get however they feel, and then we would be changing that accordingly. So I'm really impressed. It's 7:40. Before we go, I'd like to leave you there. I mean, thanks for coming. This is my notes. This is a long list of Colab notebooks, GitHub repositories, papers, articles, videos, books, and stuff to read about AI, mainly for creating all of these things I've been creating. So I'll leave you with that link now, probably in the chat. And that was it. Please ask some questions.